you could say the big picture of differential calculus is what I emphasized, I don't remember, about a week ago or something. You could say it's local linearity. The fact that when you've got a nice function whose graph is continuous, no breaks in the graph, and smooth, no corners in the graph, also no vertical tangent lines, that does happen sometimes, like with the cube root of x. Some nice graph that, well, such a graph is locally linear. It's almost as if the curve is made up of a bunch of little line segments that are really tiny, microscopic. It's like, you know, if you look at near this curve, near any point, closer and closer with a microscope, it's going to look straighter and straighter. That's what we were illustrating with Mathematica 20, 30 minutes ago, right? We were zooming in near the curve. It looks straighter and straighter. Is it straight if it's a curve? Probably not. Not exactly straight. It just looks straighter and straighter. So in our imaginations, we imagine, and Newton and Leibniz did this, they imagined that curves are made up of infinitesimally tiny straight line segments. That's local linearity. Is it really what's going on? No. But that was their imagination. And the imagination is worthwhile for intuition about what calculus is about, and including its applications. We have local linearity. I circled one point in particular, but on this smooth curve, I could have circled any point. The graph looks more and more like its tangent line near any point on a smooth curve, but different points give you different tangent lines, right? With different slopes. And of course, different y-intercepts too. This red line is the tangent line. Now, a physicist would approach this and say, yes, the tangent line is the line that the curve looks more and more like as you zoom in. And that's what the way we've been mostly thinking about it. But technically speaking, to define what the tangent line is, you can't just take a geometric intuition and say that's a definition. You have to have an analytic definition, a symbolic definition that can be calculated. And that's where limits come into play. That's going back to chapter 2. If this value of x has a name, call it x equals a, the derivative f prime of a is this limit if the limit exists. It's a two-sided limit. The limit is h goes to 0 of f of a plus h minus f of a divided by h. You had to be able to calculate those kinds of things in the first exam. Could it be on the second exam? I'm not ruling it out. So practice a few limit problems. Okay, maybe like the one in the first exam, you could go back and redo that one. There was a physics problem, I think, as well. But you should also understand the concept. F is differentiable at A. Differentiability is a new concept since exam 1. If f prime of a exists, if this limit, as again a two-sided limit, h can approach 0 from the right or from the left, exists. Most of our nice functions are smooth, differentiable everywhere they're defined. This limit does exist for power functions, for polynomial functions, for exponential functions, for cosine and sine, tangent and secant, where they're defined at least. Tangent and secant are undefined at certain places. They have vertical asymptotes. Rational functions like 1 over x, same as x to the negative 1 power, or maybe something more complicated with polynomials in the top and the bottom. They're continuous and differentiable everywhere they're defined. Everywhere they're defined, the graph is continuous and smooth. Yes, you can have vertical asymptotes. Yes, you can have holes in the graph, but those are spots where the functions are undefined. Everywhere else, they are continuous and smooth, where they're defined. Though that takes proof. You know, we didn't prove everything fully. That's the conceptual idea of the derivative. Back in chapter 2, we applied that to problems, for example, where you were thinking about really linear approximations in application problems without being real formal about linear approximations. I'm thinking of, for example, these types of problems. The cost C in dollars to produce G gallons of a chemical is a function, C equals F of G. Explain the meanings of these symbols. F of 200 is 1300 and F prime of 200 is 6. Explain the meaning of those equations. I often put problems like this on exam too. So for example, for this example, F of 200 is 1300. That means when G is 200, C is 1300. Meaning if you want to produce 200 gallons, it's going to cost you $1,300. F prime of 200 being 6 is a little trickier. It's helpful in that case to also think about it with Leibniz notation. F prime of 200 could also be written as with these given variables, dc dg. It's always the rate of change of the dependent variable, usually y, with respect to the independent variable, usually x. But in this context, with g and c as the variables, it would be dc dg. Evaluated at g equals 200. This is 6. When you write it in Leibniz notation, which you should feel comfortable with, it reminds you the derivative is a rate of change. How fast is the cost changing with respect to the gallons produced? And it's saying that when you produce 200 gallons, that rate of change is 6. Units would be dollars per gallon. And that's the basis for then approximating F of 201 to be F of 200 plus 6 times 1. Because you increase the gallons produced by 1 unit from 200 gallons to 201 gallons. So the cost is going to go up by about $6 from $1,300 to $1,306. If you increase the gallons produced by 2 to 202, then you'd have to take 6 times 2 instead of 6 times 1 and get 1,300 plus 12. $1,312 is your estimate based on really a linear approximation using the derivative as a rate of change. These equations, which we did think about back in chapter 2, are really special cases of the more general equation we've talked about more recently, where I wrote this kind of thing. F of x, well, I even use the notation, is approximately L of x, where L was a linear function, that's why it's called L. F of a plus f prime of a times x minus a. We've done that recently. In the context of this problem from chapter 2, a is 200, where we know the derivative value. X here is 201, and here it's 202. I can have different x's. I've got f of a, f of 200. F prime of a in both spots is 6. F prime of 200 is 6. And x minus a is 1 here and 2 there. 201 minus 200 is 1. 202 minus 200 is 2. I'm using really this formula that we never wrote down until later in chapter 3. We're using the tangent line to approximate the curve. The true cost curve, who knows? It could be concave up, it could be concave down. Actually, they say in economics textbooks that cost curves in this kind of situation are often concave down at first, but then concave up later. And there's good economic reasons for that. You like when you're producing gallons of this chemical in your factory, it doesn't, and you've made some certain number of gallons, it doesn't cost much more to make the next gallon when your factory has lots of capacity. But as you make more and more gallons, maybe you reach the capacity of the factory, and if you try to make another gallon, it costs a lot more. Maybe because you have to make a whole new factory. Okay, that's a little extreme. But you know, if you got lots of factories over the entire world as an averaged kind of thing, maybe that's accurate. Okay. We don't know anything about the second derivative for that example. We don't know where on this curve we are. But in any case, we're using, when we use this kind of approximation, no matter where we are, we're using a tangent line to approximate the curve. If it happens to be a spot where the curve is concave down, then the tangent line approximation is going to be too big. See, the line is above the curve. And if it happens to be at a spot where the curve is concave up, then the tangent line approximation is going to be too small. You should understand that too. Okay, these are basic applications of calculus that did come up again in chapter 3 with particular formulas. Back in chapter 2, we were just thinking about it with words or maybe with graphs, not so much with formulas. Chapter 3, we got into formulas. These are basic applications of calculus. After exam 2, next week, we get deeper into chapter 4, much more in-depth applications of differential calculus. Optimization being the big one. Another big one's called related rates. Those are big, important applications of differential calculus. These are more basic ideas. I'm not saying that means they're easy. Okay, people still have difficulty with them. But if you're going to understand the more advanced things, you got to understand the basics. And yeah, in chapter 3, we did get into more depth with particular functions and particular rules. What are the derivative rules? For computing derivatives, we've got linearity, all these derivative rules. Well, I guess the first one we said was the power rule. Power rule. The derivative with respect to x of x to the n power, where n is a constant, is n times x to the n minus 1. Right? That's the one that everybody remembers even when they're 80 years old. Took calculus 60 years ago. Okay, maybe you remember the power rule. There's also linearity. The fact that the derivative of some constant c1 times a function f plus some other constant c2 times some other function g. Those constants just stay there. You take the derivative of f and g individually and you add the result. Such an expression like this is called a linear combination. Linear combo is what I'm trying to write here of the functions f and g. If you end up taking a class called linear algebra, you learn all about linear combinations of vectors, but this is a linear combination of functions. This is something you end up using all the time without even really thinking about it, but it sure is good that it works, because calculus would be a lot harder if it didn't work, and differential equations would be a lot harder if it didn't work. It's got a physical analog, by the way. In physics, you learn about the superposition principle, for example, with waves. And the idea there is if you've got one wave going one direction and another wave going the other direction, and they meet in the middle, they, what's the word? They interfere with each other, and the resulting wave is the sum of the two waves. Effectively, it's kind of like this. You could call this a superposition principle as well. We've got the product rule. These rules you should know, not just to take individual derivatives, but you should know them in the abstract, the way I'm writing them down right now. So the derivative of a product, f of x times g of x, a left function, times a right function, or a first function times a second function. You could say the answer is left d right plus right d left, if you like. Of course, addition and multiplication are commutative. I could switch the order of these around. I could also here have f prime of x times g of x instead. But this would be how you'd want to write it if you wanted it in your mind to say lefty right plus righty left. With the quotient rule, you're taking the derivative of a quotient, a fraction, call it a ratio. You got a high function and a low function. It's low d high minus high d low over the square of what's below for the rhyming effect, or the flowing effect, I say below. And there, the minus sign, subtraction is not commutative. So the order matters in the numerator. But wait a minute, isn't subtraction also addition? And addition is commutative, right? Isn't 5 minus 2 the same as 5 plus negative 2? So why isn't subtraction commutative if addition is? It's because 2 minus 5 means something different. It means 2 plus negative 5, and those are different things. That's why. Okay, little arithmetic sidelight. Chain rule. The derivative with respect to x of a composition, f of g of x, you've got an inside function g, you've got an outside function f. The chain rule says, and I always think this in my mind, take the derivative of the outside function, f prime, plug in the inside function, then multiply times the derivative of the inside function. Common mistakes are to think the answer is f prime of g prime. No. Another common mistake is to think it's f prime of x times g prime of x. No. It's f prime of g of x times g prime of x. Those are the abstract rules. Then we have lots of particular rules, like the derivative of exponential functions. I won't list these as part of the general rules. B to the x is natural log of b times b to the x. The derivative of trig functions, cosine and sine especially, but also tangent and secant are maybe worth memorizing. The derivative of a natural log of x is 1 over x. That's worth memorizing. Without writing them down, the derivatives of inverse sine, also called arcsine, inverse tangent, also called arctangent, are worth memorizing. To tell you the truth, those derivatives are most worth memorizing because of corresponding facts that are useful for indefinite integrals. I did spend a day talking about the basics of indefinite integrals. Never assigned, or did I assign 2 homework? I guess I assigned 2 homework problems about this. They were a little tricky. You should know what this symbol means. It's called an indefinite integral. And you should know that, for example, if I write something like this, we are after the most general antiderivative of that function. That's what this is asking for. Pretend this integral thing is talking to you. And it's saying, give me the most general antiderivative of 1 over 1 plus x squared. Give me the most general function whose derivative is 1 over 1 plus x squared. If you didn't know that the derivative of inverse tangent is 1 over 1 plus x squared, you'd have no idea what to do. But you do know that. So it's actually a very easy problem. Inverse tangent of x plus c, done. Which could also be written as arctangent of x plus c, once again, because inverse tangent and arctangent mean the same thing. And inverse tangent of x does not equal tangent of x to the negative 1 power. It's unfortunate that this notation is ambiguous that way. Tangent of x to the negative 1 power is 1 over tangent of x, which is the cotangent function. And it's a different function than the inverse tangent function. It's not a negative 1 power. It's an inverse function symbol. You got to know from the context and from usage what it means. A simpler example where it might be easy to remember is indefinite integral of, say, x cubed, though that's also a little tricky. It's not x to the 4th plus c because the derivative of x to the 4th is 4x cubed. But I can easily compensate by putting a 1/4 there. That is now a function whose derivative is x cubed. The plus c should be there to give you your most general answer. C is an arbitrary constant.
Like on a question like that, you forget the plus c, like what if you have a problem right out again?
If it were 4 points, you probably get 3 out of 4. If the rest of it's right. If there were 2 points, maybe 1.5 out of 2. Okay, I don't know. I'm not guaranteeing anything. Let's spend our last 6 minutes emphasizing a harder topic, implicit differentiation, and its relationship again to multivariable calculus. Let's say we've got a multivariable calculus function. Z equals f of xy equals, let's say it's x cubed, plus x squared times y plus, or maybe y cubed plus y squared. Okay. This is a multivariable calculus function. One basic thing you should be able to do with this is you should be able to plug in numbers and see what the output is. For example, if x is 1 and y is 1, what is the output? It's 1 cubed plus 1 squared times 1 cubed plus 1 squared, okay? I made it easy on myself. Bunch of ones, the output is 3. Okay, so that's the simplest thing you could do. You should also understand, though not necessarily draw, because it would be too hard, that equation, let me first type the function in here. Oops, no and symbol. So f of 1 is 3. You should understand that the equation f of xy equals 3 can be plotted. In Mathematica or other things. And I'm going to set this equal to 3, double equal signs. There's the curve. All the points on that curve satisfy that equation. Those are the points where the output of this function is 3, including the point 1 run, right about there. Now, other points could give you different outputs, and when you make the entire contour plot, then you're looking at a bunch of different level curves, they're called, showing you how the multivariable calculus function varies. It's high values over here where the outputs are lighter in shading and low values over here where it's darker. As far as implicit differentiation goes, we can, for example, use implicit differentiation to find the slope of the curve at 1, 1. Looks like it'll be close to -1. Do I have time to find it? Let's go ahead and try. So take this equation, x cubed plus x squared, y cubed plus y squared equals 3, and assume y is a function of x, differentiate both sides using the chain rule and product rule here, based on that assumption, and solve for dy dx, and then plug in the point and see what slope we get. Hopefully it'll be close to -1. So you differentiate everything with respect to x. The derivative of x cubed is 3x squared. Here I need the product rule x squared times y cubed. I've got the product of two functions really of x because I'm assuming y depends on x. Left d right will be x squared times 3y squared times, don't forget, dy dx. I'm really using the chain rule there because y is a function of x. You could replace it with an f of x if you like, or a g of x since you've already defined f. If I replaced each y with a g of x, this would be like a g prime of x here. Don't forget to finish the product rule, though. The next thing is right d left. The derivative of x squared is 2x, and then the right is just y cubed. The derivative of y squared with respect to x is 2y times dy dx. Once again, chain rules being used. The derivative of 3 is 0. My assumption means everything, assuming y is a function of x. Solve this equation for dy dx. I'm doing it real quick because we're almost out of time. This is what you should get in general. Then you plug in the point. Again, hopefully we get something close to -1. How about that? Yeah, -5/5, -1, exactly -1. That was the slope at that point, -1 exactly. I made the numbers work out nice, okay? The assumption that y is a function of x is essential. And it doesn't matter that this graph doesn't pass the vertical line test because pieces of it do. If I focus near this point, that piece passes the vertical line test. I ignore everything else. Okay? Have a good day.